Morning, this is Mr. Weisfeld. I'm sorry I can't be with you again today. We're going over section 3.5 in the book. You went over section 3.4 the other day, and so we're going to move on to section 3.5. If you want to open your book or go to Google Drive, download the chapter, refer to page 3.5, or refer to section 3.5. We're studying kinematics. It's the description of motion. There's three equations that all physics students have to learn. So we're going to bite the bullet today and get them down. The first one, let's see. The first one here we have already talked about. It's basically the definition of acceleration. Remember, this is the final velocity, and then this is the initial velocity. If you subtract the initial velocity from the final velocity divided by time, you have acceleration. So I call this the definition of acceleration. Def, we'll call it. This one right here is the average velocity. You covered this one yesterday. What you get is the initial velocity plus the final velocity divided by 2 is average. So this is pretty easy, average. This is actually not one of the big ones that you have to know or that you use a lot. This one actually doesn't come up very much after this derivation. The point is, we want to know what the distance is that something could travel given initial or final velocity. And so the distance an object travels here is the average velocity times time. That makes sense. Velocity times time is distance. And we know that the average velocity from this equation is 1/2 initial velocity plus the final velocity. Okay, so remember, this is a game we're going to play. We're going to take equations. We're going to notice that they're expressed with certain variables, with certain quantities, physical quantities. We're going to plug them into these other equations and then get a brand new equation. The difference between these equations is what's in them. So for instance, let's go to the next slide. The next slide has distance now, but it is only in terms of velocity, acceleration, and time. So if you give me initial velocity and you tell me the acceleration and the time, I can tell you the total distance that an object has traveled. And how do I do that? Well, I take the equation that we left off with in the last slide. So distance is 1/2 initial velocity plus the final velocity times 1/2 times time. The point is, this equation here for final velocity, we got from that first equation. In other words, we got that from the definition of acceleration. So let me just write definition here. Alright, so once again, you take the simplest equation possible. What's average velocity? 1/2 times initial plus final. You take that equation, but you plug in another relationship that tells you what velocity final is. This is a relationship here. Final velocity is equal to initial velocity plus acceleration times time. So in a sense, you're adding this relationship that tells you what final velocity is in terms of acceleration, time, and initial velocity. Plug that in, simplify a little bit, and you get this equation. Now you might say, oh dang, there's time squared. Oh. Well, I call this equation the parabola equation because anytime you're taking something to a square power, you should think it's a parabola. Writing this here, parabola, so we remember it. So that's the parabola equation because it's got time, a linear term in time, time to the first power, and it's got a square term, time to the square power. How can we remember this? Let's go to the next slide here. Go back to velocity versus time. You'll recall we had things that look like this. Here's a velocity versus time curve. And what I want you to do, since we're trying to learn this equation right here, if I can find all of these parts of this equation down here in the graphical representation up here, then hopefully, the theory goes, you'll understand where this equation comes from. This equation down here, and the parabola we call it. I call it the parabola equation. You'll remember where that one comes from, and you'll remember how you can use it. So here we go. The distance an object travels. Let's just say there's no acceleration, so take this term out for a second. Distance equals velocity times time. Boom. That's actually, let me use a different color here. All right. So when I'm talking about this term right here, light blue term, I'm basically talking about this rectangle. I think I might have mentioned this on Monday when I was in class. This is velocity, constant velocity, initial velocity times time. The area under the velocity time curve is the distance you traveled. That's kind of, we give you that. You have to just assume that, or you have to believe that, but I think you realize that if you're going 30 miles an hour for 1 hour, you go 30 miles, and this is a graphical representation of 30 miles. And it has the units of miles because it's a velocity times the time. So now, let me change the color again. So now this term, the total distance I traveled is something up here plus that light blue part. So what's this part right here? Well, it's a triangle. And a triangle is 1/2, so that explains where the 1/2 comes from. The base, well, the base is just time. That explains where one of the times come from. And the height, well, this we agreed was the height of that triangle. It's the acceleration, the slope of the line. Remember, the slope of a velocity time curve is acceleration times the run, right? The slope times the run is the rise. Okay, so what I'm hoping to do from this slide, or what I hope I've done from this slide, is to show you that the distance an object travels is two parts, a rectangle part and a triangle part. This right here is the rectangle part, and the purple, you get a parabola because the changing of your velocity is depending on time, and also the time that you're traveling is a factor, so that's why you get a square. All right, so let's see. How might we apply this? Hang on just a second. We'll apply it in a second. Let's see how this looks in distance versus time. So this is the discussion in the book. Distance versus time. Recall, distance is a linear relationship of velocity and time. In other words, if you're going 30 miles an hour, wrong color. If you're going 30 miles an hour for 1 hour, you're going 30 miles. At the end, the height here that you've traveled is 30 miles. The slope, now I'm in a distance versus time graph, so pause, make sure that's clear. The slope of a distance versus time graph is velocity, so velocity times time. So I have one term right here, that's this part here. Now this is a triangle here, so that's why things get confusing, I get you. The purple part is this additional. At each time you have gone a little faster, and the faster you're going is getting faster, so the speed is getting greater each time. So that's a quadratic term. So this is a quadratic term. So you add the quadratic term to the linear term, you get this kind of parabolic motion. So this final curve right here, final curve we're talking about here, the distance you traveled under constant acceleration, distance you traveled is red, is the sum of blue and purple. In other words, it's a linear term, and it's then this quadratic term. Let me make this a little clearer. This is your quadratic term. This is those added, which overall looks parabolic. So, anytime you see something that's nonlinear in a displacement time curve, it means you've got some acceleration going on. And if it's parabolic, it's constant acceleration. I think that's what this paragraph is trying to say. I thought I would doodle on there a little bit. So distance is parabolic when you have constant acceleration. All right, next one. Let's apply this. Let's do a problem. According to Road and Track magazine, a Lotus Esprit Super Coupe can travel a straight line, right? So 100 feet, so 30.48 meters from rest in 3.30 seconds. Assume the acceleration is constant, so that tells you something. as it nearly is, determine what the acceleration is in meters per second squared. So, translation. Remember, these steps are going to help. If you can do the translation, give and find, type of problem, procedure, and calculation. If we can do that, I think you can keep your way in this class. We're finding constant acceleration from distance, initial velocity, and time. We're given the distance, initial velocity 0. You have to get that from the words. It's not necessarily written out for you, but it's in the words. And the final time is 3.3 seconds. So I hope you're seeing in your mind, let me just draw this real quick. I hope you're seeing a situation. I've got time versus velocity. I start at 0. I'm accelerating linearly. At the end of a certain amount of time, I've got a final velocity. Boom. Okay. So that's a situation, but what's the distance? All right, so let's do this. We're supposed to find acceleration. And we assume it's constant. The problem is kinematics, it's constant acceleration. So we've got constant acceleration, that's what we're supposed to find from distance, initial velocity, and time. Alright, so when you're given the distance, initial velocity, and time, use that equation 3.9. The equation 3.9 is the parabola one. You've got distance, initial velocity, time, and you can solve for acceleration. So here's the key equation that you want to remember when you see this type of given combination. Distance, check. Initial velocity, check. Time, check. And check. It's right here too. And we need to find acceleration. Alright. So, rearrange this equation. If VI is 0, this term drops out. Let me just drop that term out. This term drops out. So you get S equals 1/2 a sub t squared, so the tangential acceleration. Solving for a sub t, it's 2 times s divided by t squared. So once you get that final relationship, at is 2 times s the distance divided by the time, 3.30 seconds squared, for around 5.6 meters per second. Actually, that's wrong. Let me put this acceleration as meters per second squared, so I got to write a little squared there. Okay, so I'm solving a problem for finding acceleration given distance and given some time. Alright. So it's like, hey, my car, you could take your car out. I went from one end of the parking lot to the other in 5 minutes. I know that distance. I know what the acceleration of my car is if it's a constant acceleration. So you can see kind of the practicality of that arrangement of things. Final bit of derivation for this chapter. What you've got is the previous equation. You've got s in terms of distance, in terms of velocity, acceleration, and time. What you might like to do is you might like to replace acceleration, remove time from the equation. So what they do in order to do that, they take the time, this is the definition. This is the definition of acceleration. Remember, it's final velocity minus initial velocity divided by time, but in this case it's divided by acceleration, tangential acceleration. Substitute that into this equation, which remember is distance if you know your average velocity. So they plug in a time, and they plug in another time here. Oh, I'm seeing here that they, yes, they're plugging in average velocity times time. So remember, distance equals average velocity. This is average velocity. See the average velocity initial plus velocity final divided by 2. And then this is the equation right up here that they've got. Yeah, this is the average velocity times the time. So this is the distance you traveled, average velocity times the time. Plug that in, do some multiplication and some simplifications, you get this equation. I call this equation the no time equation. So anywhere you're talking about accelerations, velocities, distances, but there's no time involved, this is the equation you want to use, called no time. So let's apply this equation in an example. So the fastest animal sprinter is the cheetah, reaching speeds in excess of 113 kilometers per hour, so 70 miles per hour. These animals have been observed on a straight run to bound from a standing start to 72 kilometers an hour in 2 seconds. That's outstanding, right? 2 questions. Use the data to compute the magnitude of the acceleration, assuming the acceleration is constant. And then, what's the minimum distance required for the cheetah to go from rest to 17.9? So let's talk about the 2 problems together for a second, but then we have to solve them separately. Translation. All right, for part A, find the acceleration given initial velocity, final velocity, and time. Then, find the distance traveled during that acceleration. All right, here's my given. Given initial velocity, 0, so standing start for the cheetah. Final velocity, 72 kilometers per hour. This right here is important. This is distracting. I've got standing start, initial velocity, final velocity, and time. So that's what I've got right here. Don't let it confuse you. Finding the average acceleration is what I'm supposed to find. Initial velocity, final velocity, acceleration constant. Oh, sorry. The next question is, given the initial velocity, 0, final velocity, 17.9, and that the acceleration is constant, probably from this first problem, we'll use that acceleration, but they don't want to give you the time. So B, take note, they are not going to give you time in part B. No time. So that suggests that we're going to use this last equation that we just derived. So here we go. Find the distance. So distance, initial velocity, final velocity, acceleration, but no time means we use that other equation. So let's solve part A first. Initial velocity 0, final velocity 72, time 2 seconds. Find average acceleration. This is a kinematics problem, constant acceleration. By repeating this, we get good at recognizing these problems. Use the definition of acceleration, right? Acceleration in a tangential direction, straight line, we're assuming. Velocity final minus velocity initial over time. So check this out. You've got final velocity, but you have to convert to meters per second using these factors, minus the initial velocity over 2 seconds. So you multiply this out, you get 20 meters per second divided by 2 seconds, you get 10 meters per second squared. So, first part of the question, relatively straightforward. We've done this already in this chapter. Calculate acceleration given initial and final velocity and time. All right, now, second part of the question. You're given the initial velocity, you're given the final velocity, and you're given the acceleration. What's the distance that the cheetah needs to get up to speed, assuming a constant acceleration? So, type of problem, kinematics, constant acceleration. Use the no time equation, Vf squared, velocity final squared, equals velocity initial squared, plus 2 times the acceleration in the tangential direction times the distance. So take some of these numbers, plug them in. Your final velocity 17.9 squared, initial velocity 0 or 0 squared, divided by the acceleration. This right here was the acceleration that I had in the previous problem, 10 meters per second squared. That you can assume if you're given problems like this all together, and we're dividing by 2. So 17.9 squared divided by 20 essentially is 16 meters. So a meter is a little more than 3 feet, so you're about 48, maybe 50 feet. A cheetah is running 40 miles an hour at you or chasing you. So, fastest mammal on the planet. All right, so those were 2 examples, basically using the equations that we need to get good at as of this section in the book. So the first one, definition of acceleration. Final velocity equals initial velocity plus acceleration times time. The parabola equation, Remember, it came from the distance. It came from this is a triangle. So initial velocity times time plus 1/2 times the acceleration, t squared. So remember, these are kinematics, constant acceleration problems. And then the no time equation basically says that the squares of the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the distance. So no time. Time does not appear anywhere in there. And so you can use that equation in certain instances where you can't use this equation, etc. So, thank you so much for your attention. That was section 3.5. You have a homework assignment for tonight and then a quiz tomorrow. I'll be back tomorrow. Thank you.